In this video, we're going to look at the flow of current, electric current through a wire from an energetic perspective. So to do so, we think of our wire, which can be thought of with this plot here. So we think we have a wire, we have 2 points, this is point A, this is point B. In point A we have a potential of VA, in point B we have a potential of V sub B. And then as there is this potential drop, where the potential in A is bigger than the potential in B, is equivalent to saying that we have established an electric field between these 2 points that's pointing towards point V. So this electric field is going to accelerate the charges, and the total charge is going to move, if we think it's a positive charge, it's going to move towards B. So this is at some instant. If we think in a little time later, after delta t has passed, then we have that this amount of charge has moved to the right. So we had here point A, here we have point B, and if you see there is a certain amount of charge, this little piece here, that we can call delta Q, that has passed through A, and at the same time, because there is the charge cannot appear or disappear, there is a conservation of charge, and we're thinking that this is a steady flow. Then at the same time, this part here has been filled in by the same amount of delta Q that came from outside. So this is equivalent to what is shown in this figure C, in which what we have is that an amount of charge given by delta Q has passed from having a potential given by V sub B, V sub A, to a potential given by V sub B. Okay, so this is equivalent to saying that there has been some change in the energy of this delta Q. So this delta Q has changed its energy, and this we can calculate easily because if you remember from Unit 12, the change in the electric energy is going to be given by the total charge times the change of potential. So this would be potential in the end, which is B, minus the potential at A. Okay. So if we define B as the potential difference between A and B, because we know that A has greater potential than B, so V is the potential drop between A and B, then this is equivalent to saying that the change of energy that we've had in this system is equal to minus delta Q times V, because this is equal to minus V. Okay, so this minus means that there's been a loss of energy, and this is quite clear from the drawing, because we had some delta Q that passed from having a potential V sub A to potential V sub B. So there's been a loss of energy. Here you have it in equations. This is the same equation we were looking at before. This is the delta Q times V. Okay, so during time delta T, there's been this a loss of energy, and this we can measure better with the power. If you remember from the first semester, the power is the amount of energy per unit time. So if we think of the power loss, we define it directly as something negative. So the power loss is going to be the loss of energy, so it's going to be minus the change of energy divided the change of time. Then we substitute here, we can see that this is going to be delta Q divided by delta T, which is directly the amount of electric current. So we end up showing that the power loss in this segment of circuit, because there is a potential drop of V, and we have and through it we have a flow of charges that provides an electric current given by I. The power loss is I times V. Okay, if you recall Ohm's law, we know that V is equal to I times R. So we take that into account. We see that this power loss can also be expressed as square of the electric current times the resistance, and with the same idea, if from here we know that the electric current is equal to the power drop, to the potential drop divided by the resistance, then we can see that this expression is also equivalent. So just to remind you that when we have this flow of charges, if we have an electric current through a wire, then there is loss of energy. We are having a power loss that can be expressed as any of these three ways. If you remember, the units in the international system is watts, which is equal to joules, which is energy, divided by seconds. Okay, there's just one last thing I wanted to talk about, this idea of joule heating. So we've shown here that the flow of charges through this wire is losing energy. Okay, so where is this energy going? And to answer this, we have to think what is happening there microscopically. So microscopically, you can imagine the mobile charges moving because we've established an electric field. Okay, so this is going to this provides a force on the charges given by Q times E. Okay, so this is accelerating the charges. Okay, so the charges begin to move, and they can attain very big speeds in vacuum, but inside the wire is made of a conductor, so the wire is not vacuum. The wire is indeed made of a net of ions. Okay, so you have this net of ions, and you have some of the electrons that are free to move, form the mobile charges, which are accelerated, but they are not in the vacuum, so they easily easily interact with the ions of the net, and by this interaction they are slowed down. The mobile charges, the electrons are slowed down, and the excess of energy is provided to the ions in a way that it makes them vibrate. So this vibration is really heating. So what is happening here is that this flow of charges of electric current through the wire can also be seen as a conversion of electric energy into a different type of energy that is heating. Okay, so this is what we call Joule effect or Joule heating, and is the basic that's used in the common ceramic stoves that you might have at home to cook. So in these stoves, what we have is a big resistor through which we apply an electric current, and this electric current is transforming electric energy into heating. Okay, it's heating the resistor, and this heating is used for cooking.